Good morning. Okay, let's settle down here. Okay, just a quick review on the impulse response of LTI system, linear time invariant system. We have introduced a very important theorem at the end of the last lecture. First of all, we introduced the concept of impulse response. An impulse response is basically the response when the input is impulse. Okay? So this is what impulse response is. So impulse response is the system output when input is an impulse signal. And we use h of t to represent this impulse response. Instead of a general y of t as output, we use a special dedicated symbol h of t to represent this impulse response. And now the theorem basically says, if you change the input to anything else, call it x of t, then you don't have to actually do an actual experiment. Yes. Yeah, that should do it. Excellent. Thank you. Yeah. So you can actually mathematically calculate the system output by convoluting the current input x of t with the impulse response h of t. Okay, so that essentially what this theorem says for LTI system. Okay? Yeah. This is a very useful one because, as you can see, as I explained, if you have the impulse response, then literally you can just convolute whatever the current input is, then you get the current output. Right? You don't even have to do an experiment. You don't even have to, explain, because that's what the theory says. Okay? LTI system. Okay. Now, in the future, we'll learn how to obtain h of t. Okay? So basically, there's a question: how to obtain h of t, or impulse response. Now, there are two different approaches to obtain. Approach number one is a theoretical approach. Okay. Theoretical approach, without giving too much details, basically we can solve a differential equation. That differential equation will be used to describe the system. So we can solve a differential equation to get mathematically the impulse response. And approach number one is more of a practical approach. Okay. A practical approach is what I mentioned at the end of the lecture. If the impulse response is the system output when input is impulse signal, then you have to give the system an impulse signal as input. However, impulse signal, as we learned, is a signal that has an infinite amount of magnitude at t equal to 0, right? And that literally is impossible to obtain in actual practical case, in reality. You cannot have a signal that have infinite, magnitude, right? So what can you do? You can only use some input that's approximately acting as if it's an impulse. One of the examples I give you, you could generate maybe like a momentarily a punch or hammer, right? That generates basically an impulse. Okay? Mathematically, you could, or you would use a circuit or use a certain, generator. You could also generate impulse, but that's not the actual infinite magnitude impulse. Okay. So as approximation of the impulse signal. So it's not going to be a perfect impulse response. It's just going to be a approximate one. So this one here, what you get will be approximate solution. Okay. But this one here, that will be an exact solution. Okay. So we'll see actually particular this approach number 1. Okay, when we introduce the differential equation. Okay, but what I want to do next is I want to give an example by applying this theorem to an LTI system. So here's an example here. Okay, this is a very typical question that you could see in the midterm. The question could see that if input x of t is delta t. Interpret every one of the words here appropriately. Okay, so when we say input x of t equal to delta t, using wording meaning the input is what? Impulse signal. Okay, very good. And output is y of t equal to e to the power negative t times u of t. Okay, that's the given condition, right? So the first simple question, what is the impulse response? H of t. It's a very, very simple one, but every year I got students actually got stuck on this question. So if your input is this and your output is this, what is the impulse response? That is impulse response, exactly, right? You don't have to hesitate. There's no trick at all, right? I'm just testing you the definition of impulse response. When input is the impulse, the corresponding output is called impulse response. What do? You don't have to do anything. Just rewrite the outputs. Okay, that's your impulse response. Exactly the definition of what impulse response is. Okay, and now a second part of the question typically will be, if I change the input to something else now, if the input is this time x of t equal to this one, okay, exponential decay function time u of t, and what is output? Okay. Exactly. Right? So now you can see we're combining the convolution with this theorem now, right? So you end up with doing a convolution exercise basically. Okay? So y of t equal to x of t convolute h of t according to the LTI, the theorem. Okay? And the other thing I think for now you can see we're combining different things together. Okay? Yeah. First of all, I'm giving you an output function which actually involves the unit step function here, and for both cases. And then you have a convolution, right? So there's a couple things involved here. So it should actually jog your mind now. When you have a function like this, basically, first part is a time function or t function, time u of t. So u of t is unit step function. Anything time u of t will give you what kind of signal? Causal signal, right? Because your left side of the signal will be gone, only the right side is left, right? Because that's what time u of t would do. Okay? Yeah. So this gives you a causal signal. So I didn't graph anything at here, right? So in the previous examples, we typically give you the graph. Here's function f, graph. Here's function g, and another graph. But this time, I give you an expression. And it's up to you to actually graph this out, okay? Because when you do the convolution, you'll use the graphical approach, and you'll end up graphing the function set here, okay? Okay, so I'll show you how to do this kind of question. Not just the graph, actually I will use all the expressions at here, okay, during the process. So we're solving this one at here. We're going to pick this as x of t, and this is as h of t, right? H of t here. Okay. So graphical approach meaning we will graph x of tau. Okay. So this is x of tau, the current input. And if you recall that in the first lecture, I specifically mentioned you need to be able to sketch very basic functions. One of them is this kind of exponential function, right? Sketching function means sometimes you need to pick a special point to give you an indication, how does the function behave in the coordinate system. So we're talking about x tau and tau at here. Okay. So x of tau, you replace the t with tau. Okay. So find everywhere, find the tau, find the t, and replace them with tau. Okay. Let's graph this one, right? Graph this one. Essentially, we're not going to worry about anything on the left side. It's only going to be this side. So the one of the special point is you can always let the tau equal to 0. So let tau equal to 0 and see what does that value equal to. So when you let the tau equal to 0, you get e to the power -2 times -3, and which is e to the power 6. Okay. So basically, when tau equal to 0, your x of tau equal to e to the power of 6. Then, as tau goes up, goes more and more bigger, okay, it's just a downhill. It will keep going down. Okay. So this part, it doesn't have to be very accurate. Okay. That's just rough sketch, and that's fine. Okay. Yeah. All right. So that is x of tau. That's it, right? Now let's deal with h of t. So the idea is first h of tau, then h of negative tau, then h of what? Negative tau minus t. So these 3 steps. Okay, so I'm going to draw it over here, and then I'll bring back over here to try to find overlap. First, h of tau, so that part is easy. H of tau, it's downhill here. What is h of tau? H of tau is over here. So h of tau equal to e to the power negative tau u tau. Okay. Again, find the special points at the tau equal to 0. So when tau equal to 0, e to the power 0 is 1. So that's just 1 over here. Okay. So notice that the little subtle difference is I'm not just sketching this one here. I'm actually also keeping the exact expression, right? With even this, not just this part, but also the unit step function in the picture. Okay, so now let's look at what is h of negative tau. Okay. H of negative tau is the mirror of this one. Okay. It's the mirror of this curve. Okay. And then next is shifting. H of negative tau minus t. Okay. So maybe I'll write down here. So the expression wise, what's h of negative tau? This is h of tau at here. If we change the tau to negative tau, then we go to the right side, find all the taus, and change the tau to negative tau. Okay, so this is you get the exact solution here, right? Okay, and this is equal to e to the power of tau and u negative tau times u negative tau. So basically, this curve, okay, is this. But also, I think at this stage, you should also be clear, right? For example, if I give you a curve like this, if I give you a curve maybe without this, just this portion, if I give you a curve like that, and you know exactly for this curve, it's what, e to the power of negative tau, right? Yeah. But if I give you this, just a blue one, and you know that it's this one, okay? However, you also know for any points here, here, here on this part of the curve, the value of the point is given by what? E to the power negative tau, okay? Yeah. So even though you do have the u at here, the u is just indicating it's a causal signal, okay? Yeah. Okay, so let's go back to over here. From h of negative tau to h of negative tau minus t, okay, to h of tau minus t. So h of tau, negative tau to h of negative tau minus t. So what is the change at here? The change is from what? The tau at here changed to tau minus t, right? So now you go to the right side. Okay, go to the right side here, find all the tau, and replace this tau. So basically, tau changed to tau minus t, So that gives us this one will give us what? E to the power. Find the tau, change to tau minus t, and then u negative tau minus t. Okay. Yeah. Graphical wise, this curve shifting to the right by amount of t. So without changing the 1 here, it shifts somewhere over here, and this is t. So this is the actual graph, and the expression for this graph is basically, well, you don't have to worry about the u. If you look at what's the point, what's the value of the point here, it's given by this, right? It's given by this. One of the assignments, I think, has a similar issue. You have a triangle, you have a box. I got some question from student. So what is the expression for the points on that triangle, the ramp, right? You get how do I get the exact expression? Because you need to multiply that function with the box. And this is actually the way you can do it. When you're going through these steps here, you're going through the substitution, and you get the expression for this curve with this. Okay? Yeah. Any questions so far? Yeah. So that's important, because if you don't get this right, then you can do the next convolution, right? You have to multiply things together. Okay. So once I get this, then I could just bring this back over here, because I need to look at overlap. So I'm going to put this x of tau and h of negative tau minus t, which is basically h of t minus tau, okay, on top of each other. Okay, so I can clearly see what kind of overlap there are between these two curves. Okay. The first type overlap is there's no overlap, right? And then the second type overlap is the overlap start to occur. Now the third is you then say, okay, is there a different patterns of overlap, right? That's basically what you're trying to navigate at here. So you could have the whole curve, okay, on the right side, on the left side there, okay, and that's when you don't have any overlap. And then this t will keep changing. So this curve will keep moving to the right. So then you would have the overlap occur now, right? Yeah. In this case, there's only one pattern overlap, because it doesn't matter how far this curve moves to the right, the overlap always happens from where to where? 0 to t, right? Overlap always happens between 0 and the t. Okay. So there's only one pattern in this case. That's lucky, right? That's good. Okay. And because this goes to infinite, as a matter of fact, you don't have any more overlap, right? Sometimes we have another overlap, we can basically go back to 0, right? But this one, no, because it's going to keep having overlap between these two. Okay. So now you can see, I will see overlap between tau between 0 and t. Okay, that's the overlap. Because you're multiplying these two functions, x of tau times this. And then, of course, you had to figure out at what value of the t that you start to have this kind of overlap, right? And that's also pretty straightforward. When this edge is on the right side of the tau equal to 0 or t equal to 0, then you get this overlap. Okay, when t is greater than 0. Okay, and that's it. So you could see, okay, when t is less than 0, the convolution is, or the output's nothing, right? It's 0. When t is greater than 0, then you have this integral, 0 to t, that's the range here. Then multiply this function with this function. Or in other words, you multiply this part with this part. Okay? So when you multiply this part with this part, you don't have to keep the u and the u of negative this part anymore, because those are, you're basically multiplying this part of curve, this part and you know what? You know that this part of curve is this, and that part of curve is this, right? So what we can do is, right, so I will write down the x of tau times h of t minus tau d tau. Okay. And x of tau is, what's x tau here? E to the power, so x of tau, where's x tau here? X tau is this. E to the power negative 2 bracket tau minus 3. Okay, that's x of tau. And h of tau, which is this part here, so e to the power tau minus t d tau. Okay. So we need to do this integral involving the exponential function. Often in time, what you could do is you can use this property. E to the power of a plus b equal to e plus a e plus b. Okay. Separating constant term and variable term out of the picture. Okay. Yeah. So here's what we're going to do. Because we're integrating with respect to tau, so I'm going to separating anything that's not related to tau. Here you have multiplying the negative 2 into the bracket. So you have a negative 2 tau and then plus e to the power 6, right? So I'll put this 6 out of here, and e to the power negative 2 tau. That's for the first term. The second term, you get e to the power of tau, e to the power of negative t at d tau. Okay. So now I have e to the power 6 and e to the power negative t. So these two terms, you can combine them together. You get e to the power 6 minus t. And these two terms combined together, you get negative tau. Okay. Because you're integrating with tau, so this term is actually considered as a constant, right? So you can move this term out of it. Okay. This is a very simple integral. You can put a negative here and then put a negative in the front, so you keep it as the same. Now you have negative tau, the same variable. Integration of e to the power of anything, give back that anything, right? So you basically get e to the power negative tau, and then 0 to t. Okay. So inside here you get e to the power negative t minus 1. Okay, minus 1. Again, simplify this a little bit more. So multiply this into the bracket. Right. So you will get e to the power 6 minus t minus e to the power 6 minus 2t. That's it. Okay. Good? Yeah. This is a typical application combining unit step function, basically piecewise function, right? And the theory of that linear time invariant system and convolution, and you exercise. Okay. So that's a very good example that can test your knowledge in terms of what is the impulse response. How do I get system output given impulse response and another input, okay? And how to calculate the convolution. Okay? Any question? Okay, good. All right, so I'll give you one more example, okay, and then we'll go to new topics. Well, start example actually it was a little bit of non-related to this impulse response. Okay. So let's say we have an LTI system. We have input x of t, and we have output y of t. Okay. Now, I want to prove. Okay, I want to prove that if the input is changed to so this time the input is, instead of x of t, the input becomes the derivative of x of t. Prove that the output, okay, the output corresponding to this input is the dy of t over dt. Okay. Yeah, that's also very useful proof sometimes you can make use of. So system input is x of t, corresponding output at y. You change the input to the derivative of original input. If it's LTI system, we will be able to prove that y2 of t is the actual derivative of the original output. Okay. So here's a simple proof. Okay. The proofs basically involve the definition of derivative. Definition of derivative says this. Right? This is a definition. So you take a shifted value x of t by h much, this time much, and then minus the x of t, and then divided by h. So give you the rate of change, right, of this around this h at around the t equal to 0. Okay. So if this is a dx over dt, basically this is what? This is your x2 of t, right? This is your x2 of t here. And x2 of t involving this limit of this. And this is where now we can make use of the properties of LTI system. Property LTI system, linearity and time invariance. So linearity says, when your input has a multiple inputs, okay, then the output is addition of the outputs corresponding to the individual inputs. And this x of t plus h, that's basically the shifting, right? It's the property where the property time invariance can be used. If you shift the input, then you shift the output. Okay? So then we make use of this to get our output here. So if our output, right, if our input is x2 of t, and basically it's m, this whole limit things. Now the limit at here actually really doesn't play anything. You can just simply take the limits, okay, out of the bracket and move the m into the bracket. Okay? Yeah. So now you can apply the linearity property and time invariance property, right? For this one here, so that this coefficient is 1 over h, and this coefficient is the negative 1 over h. That's like a C1, C2, right? The superposition. So this h can be taken out of it. And the output corresponding to x of t plus h is y of t plus h. And the output for this one here is y of t. And h, you don't change, still h. Okay. So now you get basically what? The definition, the derivative for dy over dt. Okay? So that basically is the proof. When input is x of t, your output is y, and when input is changed to derivative x of t, the output is the derivative original y of t. Okay, good. I want to make use of this conclusion actually for the second part of this question, right? Yeah. If a system has an input which is a unit step signal, and its corresponding output is given at here, okay. I should say it's LTI system. Okay. If LTI system input this, output is this signal. So this one here, sometimes we call it basically like a unit step response. So now you typically have a impulse response, right? We use h of t. There's another actually very useful one called unit step response. Okay. But there is no dedicated symbol for unit step inputs. Okay. Yeah. So now the question will be, what is the impulse response? Okay. What is the impulse response? H of t. Okay. So impulse response, according to definition, is the response when the input is what kind of signal? Impulse signal. Okay. So basically, when input is delta t, and what does that produce? All right. Okay. So I will make use of the property that we just derived here, because here the input, this is a unit step input. If this is x of t at here, and we're actually making use of another one here. If you recall that, if you take the derivative of a unit step input, what should I give you? Impulse delta t, right? Delta t here. So if this is x of t is the input, is u of t, and that's basically the proof, the result proof we can make use of. Then the h of t at here is dy over dt, right? Yeah. So you change the inputs to the impulse, which is the derivative of the original inputs x. Then the current output, which is impulse response, will be the derivative of the previous output. Okay, so now I'm taking derivative of this guy here, okay, of this guy. Okay. So this is literally just a multiplication of two parts, the bracket times u of t, right? So when you are taking derivative of a two function, multiplication two function, what do you use? Not chain rule, product rule, right? Product rule, okay? You actually probably do involve chain rule. So product rule. So derivative of the first term times u of t, and the first term times the derivative of the second term. So let's do that. What's the derivative of the first term? Negative e to the power of a negative t plus 2 times e to the power of negative 2t times u of t. Right, that's the derivative of the first term. So u prime v plus v prime u. Right. And the second term is the bracket times derivative of u of t. And derivative of u of t is delta t. Okay. And that's the results of this derivative. But you don't actually stop here. You can't do anything about this, but for this one, you can do actually a little bit something. Okay. So this is actually making use of another property for impulse response. Any function time impulse response, because the impulse signal only exists at the t equal to 0. So for this term, what do I do for this term here? We replace the t with t equal to 0. Right? Yeah. That's a simplification. And this for these two terms here is 1 minus 1. So you get a 1 minus 1 is 0. So you get a 0 times delta t. Right? 0 times delta t. So 0 times delta t, this is where it could get confused. Delta t is infinite at a t equal to 0. And then infinite times 0, what should that give us, right? So in this case, 0 trumps infinite. So this guy here will be 0. Okay? Yeah. So you're left with just this portion. That good? Yeah. So there's a little bit of a combination of different applications of the properties added here, right? Yeah. Very simple question, but you're making use of a lot of results added here. Okay. Good. In my lecture, I do have another section here called the causality, system causality and impulse response. I think I'm going to skip that. You can take a reading of that. It's only one page, or a little bit more than one page, so it's not too. I'm not going to test that in the midterm or in the final. Okay. Okay. Any questions so far? Okay. So up to this stage, up to this lecture, we basically have covered a lot of concepts on signals and the systems. We haven't talked really anything about differential equation, about system how do we describe a system using a differential equation yet. And so from this day on, we will actually go into that stage. How do we describe a system mathematically using differential equation? Okay. So I always consider this course has two parts. One part is what we covered so far. It's more on signals and systems. And the other part will be more on mathematical, which basically solving differential equations. So if you go to a math department, typically there is a course dedicated to solving ordinary differential equation, which is what we're going to do next. Okay? Yeah. But in order to do that, we do it, of course, we do it not the same as a typical math course. So we always do it using engineering concept, engineering examples. So the first thing that I have to do is, how do we construct a model? Okay? Instead of just give you a model, give you a differential equation, we will look at how that differential equation derived based on the actual physical model. Okay? So we call this part model construction. Okay? A lot of time you can also consider this a modeling. Okay? There is a huge branch called mathematical modeling. Engineering-wise, mathematical modeling has different meanings. Let's say you model the evolution of the population. That's mathematical modeling, right? But we are focusing on modeling of a physical engineering system. So, in particular, we're going to look at mass spring damper system, typical electrical RLC circuits. Right? That's what we call modeling. Okay? Yeah. So, to model a system, or to come up with the model construction, you're going to have to basically make use of physical principles. Okay. So what are the principles that you can make use of? Here's a few that you have to learn. Okay. First one, Newton's second law. So Newton's second law is a very common one to use to describe dynamics of a system, right? So Newton's second law basically says if you have mass, okay, a point mass, and then you have a whole bunch of forces, okay, applied to this mass, okay. So then when you add these forces together, okay, then the force should equal to the total, equal to the mass times the acceleration, right? So that's Newton's second law. Now acceleration, right, is indicated with A, but acceleration can be derived from position. So acceleration derived from position basically means if you derive from position x here, so that becomes x double dot. Right. So I'm using vector as an example here, but I think in a lot of time, especially in high school, a lot of time instead of a vector, all you have is all scalar case, right? So you end up with just mx double dot, right? That's a scalar. And this is the Newton's second law. In particular, okay, this one here is actually, we call that translational motion. So it moves linearly in certain direction. That's called translational motion. The object not necessarily just translational motion. The object could actually rotate. Okay, so then you have also rotational motion. Okay. Rotational motion, instead of a force, right? So force gives you translational motion. Now, when it comes to rotational motion, it will be a torque. Okay, it will be torque. So if you apply a different number of a torque, okay, to the system, and you add them all up, okay, all of the torque individually will cause rotation, but add them together, there's still kind of rotation. Force is related to the mass, and then torque is related to what? Inertia. Moment inertia. Okay. So we can use a J, sometimes use I. Okay. A J usually representing a polar moment inertia. So that's more of this. Okay. You can use I too. Okay. And translational motion deals with is the acceleration, so linear acceleration. and also the double derivative, second derivative of the displacement. Then for rotational motion, it's not the linear motion, it's the angular motion. So instead of x, it becomes theta double dot. Okay. All right. So this is the two very useful ones. Okay. A lot of very complicated mechanical system, the motion mechanical system starts from here. Right. Start from here. And that's Newton's second law, and that's mechanical wise. For electrical wise, when you have a circuit, what you do is you do have two laws. One is called Kirchhoff's current law, and the other one is the voltage law. Okay, so you can use this as the basic principle to analyze any electrical circuit. Okay. So the current law, okay, I'll write down both of these right here. Okay. So the current law basically says if you pick one node, right, and then you add up all of the currents, okay, flowing through that node, you get a total is 0. Okay. Yeah. And the voltage law says basically, okay, if you look at a loop and you add all the voltage up around the loop, and you get a 0. Okay, that's the two basic current law and voltage law. So those laws kind of governing a bigger picture, right? So you have all of this, for any kind of a circuit or any kind of a mechanical system. However, for individual components, okay, so when you come to individual components, we have specific equations or formulas governing that component. Okay, so let's take a look at some equations at here. So I guess I don't have time anymore. Anyway, so we'll talk about this. I think we're going to talk about this equation for different component next time. Okay? Yeah. All right. So the quiz 1 finishes this week. Next week, no quiz. We'll have another quiz week after, which will be on the convolution or linear LTI system, and then after another week, that'll be the midterm. Okay.